Hello and welcome to entry number 4 of my mathematical journal or mathematical diary. Sorry, I'm just having a bit of coffee. I've decided I will make this in the morning of Monday as opposed to the evening of Sunday when my brain is not mush. I had intended upon getting this out by Sunday midnight, but plans got in the way. Real life, not maths. Um, but in the time between last recording and this recording, have uh, I've read a little bit of uh, Commutative Algebra by David Eisenbud. I've gone past chapter 0, and it has struck me just how much algebraic geometry is in chapter 1, but the classical algebraic geometry, no schemes or sheaves. But I think it's just a nice treat to wane you into the book before you go into the hell of localizations. But this entry will be mostly focused upon section 0.3 of commutative algebra. I have had to bring a little bit of my lectures in, so quotient rings, just because, well, it isn't discussed within section 0, and it's used within section 0, so I thought I might, well, A, brush up on it, because I learned it 2 years ago, and B, well, write it down, because, I mean, I A said that I would, but B, a ring over an ideal makes absolutely no sense if you're just following along, because how can you divide these things? And it, yeah, I've uh, I've actually discussed this with my master's project supervisor. Just not the lowering of standards, but the lowering of what you are expected to know going into a postgraduate degree. Because I have taken basically every algebra module within my university, and I've not discussed modules. And well, I've glancingly discussed modules. I think if we have time at the very end, I will write something on that, but I uh, I doubt that we'll have time. This is usually I do 3 things, and today I've done 4, just because this will not take very long at all. And this is more of a fun thing where I kind of want to discuss this and show how this can be used to describe this. I find it fun. I think that it's fun, mostly because my master's project was mostly on category theory and how you can define a very important tool within scheme theory, or, well, within homological algebra, but scheme theory uses homology a lot. How you can define a certain tool within scheme theory category theoretic languages, via category theoretic language, and, well, that is exact sequences and complexes. In You also need something called the snake lemma, but I mean I can talk about that as a little treat at the end. I've not actually finished this slide. I intend on finishing it while I record, just because I think that that would be fun. But I think that we should probably get stuck right into it. Oh, no, there is one more thing which I wanted to say, which is Robin Hartshorne is not dead. Um, in entry number 3, I did say that Robin Hartshorne was the late professor, but no, Professor Emeritus. He is very much alive, and I deeply regret implying his death. But with that out of the way, let's just do a very quick recap in case you've either not watched entry number 3 or intend upon having large gaps in between. But yes, so an ideal is an additive subgroup of a ring such that it's a multiplicative black hole. And here are some definitions which you can give to an ideal. So it's proper if it's not the whole thing. So the ring itself is an ideal, but it doesn't really count as an ideal. It does count as an ideal, but there's not that much. It's not an interesting ideal. It's prime if you can't divide your way out of the ideal, even if division is factor your way out of the ideal. So you can factor your way out of the ideal generated by 12, which I discussed last time, but not out of the not out of the ideal generated by 2. And it is maximal if it is proper, but no other proper ideal contains it. It just so happens that 2 is both a prime ideal and a maximal ideal. And the local ring is a ring where it's got one maximal ideal, but we'll discuss that when we discuss localization. An element of a ring is a unit if you can multiply it to get 1, and a non-zero element is a zero divisor if you can multiply it by another non-zero element to get 0. A ring is a domain if it doesn't have zero divisors. A domain is a unique factorization domain if you can uniquely factor. I think there are some z adjoin square root of minus d where, okay, so this is z adjoin x such that x squared plus d equals 0. Or, in fact, I can give an alternative definition within the very first slide, so I'm not going to. An ideal is principal if it... Oh, goodness. A ring is a principal ideal domain if all of its ideals are generated by one element. So the integers are a principal ideal domain because you can say, oh look, here's an ideal generated by some set. Well, you can cut that set down by 1 each time, and you can just take the greatest common divisor of, I guess, all elements in the set, but greatest common divisor is on 2. So, for instance, the ideal generated by 56 and 14 is 2, I believe. Yeah, this is 19 times 4, and this is 7 times 2. So, yeah. And this is what is meant by principal, so you can have a principal ideal generated by multiple elements, but it doesn't really matter because you can just cut them down somewhat. But, oh, and if you'll recall back to last time, you can have ideals ij. Well, if I is generated by some set and j is generated by some other set, then, then if you multiply, well, I'm going to write s sub I and s sub j. So if an ideal is generated, if I is generated by s sub I and j is generated by s sub j, then you just take pairs in here and in here. So, for instance, I am going to stick with the integers. So, for instance, the ideal generated by 2 and the ideal generated by 3 is the ideal generated by 6. Let's rub this all out. You can divide ideals, and there is a part of section 0.3 where that construction is given. And I really should have put it in basic constructions, but I just ran out of space because there were other things which I wanted to discuss. And I kind of wanted to show how you can generalize well, slide 4, how you can generalize the notion of quotient ideals with modules, and with module homomorphisms and exact sequences, because exact sequences are precisely what you need to know to define quotients in more general spaces. So that's what well, epimorphisms are, but that's besides the point. Within categories derived from algebraic structures, mostly. So, let's continue. A commutative algebra over a commutative ring you can define to just be a ring homomorphism with, well, a set ring homomorphism. But the underlying set of the codomain is probably the best bet of how you should actually write things down. So, if R is a field, then an algebra is a vector space with a commutative associative bilinear product, which we will see later. It's a similar thing. So, last time I asked a bunch of very easy things just to get those cogs in your brain working. So, firstly, this is just define what a kernel is, and then just use the definition of a ring homomorphism. So that's easy. I'll get back to this one because this is more of a thinking one. I didn't include the Z is a unique factorization domain. That's just to look up what the fundamental theorem of arithmetic is. But again, this is just state the problem, then this just shows that you've got this is the definition of being within this ideal, and then you just use the fact that it's a prime ideal, and so just again use the fact that these are in the ideal, and just this is what that means. The very final problem which I talked about, which I gave you and wrote down the solution of, is this, which I think has a neat solution. So if you have a non-zero ideal, 0 is always an ideal within any ring. So if you have a non-zero ideal, you just need to show that 1 is within it, so then it is just the ring itself, or in this case, field. So now we discuss this, where you want to evaluate some multivariate polynomial, let's say x, y, z, or alpha 1, alpha 2, alpha 3. Well, you want to assign some ring element here. Well, that requires some level of R. Well, now you need another level of R, and now you need another level of R. So, R cubed. And this is equal because R cubed is defined to be the Cartesian product 3 times, or the categorical product. And this is a ring via this construction, so let's say this is how you write down vectors, just another way of writing it down, because this construction, there is another construction where this makes sense. And oh, and the delta, this is called the Kronecker delta, named after well, Kronecker. But it's technically a binary function on the integers, so delta of I, j, these are, well, natural numbers, but integers, and then you have either if I is j, then it's 1, and if I and j are not equal, then it's 0. And it's a nice way of just writing down, okay, if I and j are the same, then it's 1, and if I and j are not the same, then it's 0. I don't remember why it's a delta, but I guess it's just something which Kronecker chose. But let's continue on with quotient rings. This is mean of me, but it's not very difficult. And this is just, it looks like 4, it's actually 2 questions, but if we take a ring and a fixed ideal within that ring, you can define some equivalents as if you can define some equivalents of the elements of R such that 2 elements are equivalent if their difference is within an ideal. So elements of the ideal are equivalent to 0. Everything is equivalent to something. It has to be equivalent to itself at the very least. So you can have it as an element of some equivalence class. But if you have something within its equivalence class and within another equivalence class, and A equivalent to B is the same as B equivalent to A, like these are just the same statement. This double arrow just means this is the same statement restated in another way. So this is what I actually want you to show is like these two are the same statement, framed in a different way. So this means this and this means this. Well, then they are exactly the same thing. But it forms a partition because you have every single element being a thing, and also these things are completely disjoint. So for instance, the odd numbers and the even numbers. You can't have a number which is both odd and even. The multiples of 3, you can't have a number which is a multiple of 3, which is 1 more than a multiple of 3, or 2 more than a multiple of 3 at the same time. So these are just, and then these are mutually incompatible. So you can choose some representative of everything equivalent to this within the ring. And the set of those representatives is the quotient. So is R over I. So the integers over the even numbers, well, the even numbers are a maximal ideal, so it's a field. And it just so happens, oh, you've only got odd numbers, or you've got even numbers. Oh, look, as I stated last time, we will show that this is a field. It's a field. And you inherit the ring actions, so you inherit multiplication. I haven't shown it to be the case, but A plus B, well, A is representative of A within the ideal. Within the ring. B is representative of B within the ring. Well, it makes sense to represent this by just the sum. And if you just use if you use this, then yeah, this obviously makes sense. And the same for multiplication. You just think about this, and yeah, it just makes sense. There's a little red dot there, and I'm annoyed by it. But that is what the quotient field is. And you might think that within, say, z over 2, you have the issue of, oh look, you've got 0 and 2, well, they're the same thing. So sets can't have repeats. That's one of the defining things of a set. If you have a set with repeats, it's called a multiset, and that isn't a set. Set theory. There were a lot of debates in the 19th century about sets, and that was one of the things which I think is common among the different set theories. There are multiple different set theories, and I'm not going to get into it because that's just hellish to try and get into it. I'm not sure if my device is picking up my audio. No, it is. It is. Perfect. That was, oh god, I need to just throw away 20 minutes. But one thing which I want you to show is to compute this. The real numbers adjoin x over the ideal generated by x squared plus 1. And what this means is x cubed is actually x squared times x. So x cubed plus x equals 0. So x cubed is minus x. What does this look like? Have you ever seen this before? I mean, if you haven't, then good job getting through to here, but does this look like anything familiar? And in fact, that familiar thing which this does look like is this is the formal definition of it. This is well done. You have finally learned the formal definition of the thing. But note that this process may be repeated for ideals, and we will get into that in slide 4, I guess. Or considering this to be slide 1, then slide 4, it's actually slide 3. So slide 7. But we move on to modules, and if we let a if we have a ring, then an R module consists of a set, an addition, and a sort of multiplication. Addition is defined to be like addition on rings. So you have an identity element, you have negatives, you have associativity, and you have commutativity. This defines what's called an abelian group. So named after Niels or Neil. I'm not actually sure on that pronunciation. I'm not Swedish, but Neil or Niels Abel. Abes? That feels a little bit familiar. Niels Abel, who studied abelian groups a lot. And there's just loads and loads of things named after him in what's now basic group theory, but for him, cutting edge science or cutting edge maths. Maths is the queen of science, but it's not really a science because you're not trying to verify things, you're just stating, well, here is a definition, this is what these definitions mean, and here's what these definitions imply, how can we work with that? It's not really, I wonder if more leaves are brown than green. Okay, we need to collect samples. Well, what are you sampling here? But I digress. That's what an abelian group is. It's zero, negatives, associativity, and commutativity. But you need to have this multiplication R multiplied by Sm is the same as Rs within your ring multiplied by M. So this is within the module, this is within the ring. It's kind of confusing, but once you get the hang of if there's brackets all the way to the right, it's probably within the module. It works. This is technically a left module, but it doesn't. A left module and a right module, it's just convention what side you put the ring on. It doesn't really matter. Modules within algebraic geometry are left modules, just because, well, a module over a field is a vector space, and if you have, say, 1, 2, 1, you put, I'm just going to go lambda there. You you put it to the left usually, so lambda 2 lambda lambda. So most modules are left modules within most of maths, but you can have right modules. You just define this action to be MR instead of RM. But you have, I guess, quasi, but associativity, you have distributivity or bilinearity. Over, this is within M, remember, this is within R, remember. And you have 1 in your ring multiplied by any element in the module, it doesn't change. So, for instance, 1 lots of a vector over, let's say, the real numbers, it doesn't really matter. You have 1. You... I've not shown why you can write vectors like this yet. I will do on the next slide, so stay tuned. But any abelian group is itself an integer module via ng is g to the n, and most abelian groups you just write with the sign plus, but technically g to the n is g plus n times. So g squared is just g plus g. And g to the naught is e. So, if R is a field, then a module over that field is a vector space. Again, fields are written K due to the German word corpus, which means body, which meant like a whole, but that was brought into French to be like cour, and then that means field in French, so field. But given a R module, a submodule is, well, a module which is contained precisely... Oh, this is not minus, this is just an arrow. It's a module which has the same 0, and also the same... And also you can't multiply, or... This is called an action. That's... It's because it R acts upon it, but yeah, it's multiplication. It's scalar multiplication. That's another word which I've seen used for it within M.E. Keating's module theory. But the scalar multiplication is closed, so total. It doesn't... You can't get out of n by multiplication, or indeed addition. But I want you to show that a ring is itself an R module where this action is just R times R because M is R here, so and then I want you to show that an ideal is a submodule. Well, if you have an ideal, then this is just the multiplicative black hole thing. And show that a commutative algebra over a commutative ring is itself an R module. Technically, algebras are modules themselves with an additional thing, but this is all that's needed for well, last time's definition is all that's needed because we're working over commutative rings, so it all simplifies down to just a ring with a group a ring homomorphism, which is just this action. But, well, you replace R with phi of r, and because it doesn't really matter which direction you have, it doesn't work. So it doesn't work. It r goes to m, well, your other ring, so via phi of r, so it's actually m times m, and you just use the multiplication. But because we're working with commutative algebras over commutative rings, it doesn't really matter. That's a simpler definition, so, and it works within what we want, so it works. So, here are some constructions with modules. So, the most important one for us right now is the direct sum or direct product. Uh, we are working in an additive category. Sorry, yes, an additive category. So uh, the direct product and the actual Cartesian product or direct sum, it doesn't matter. It's usually written with this O plus. That implies that you're working in a categorical coproduct, but it doesn't really matter because they're the same thing. But, well, yeah, because we're working with commutative rings, so it's a subset of the category of abelian groups, so yeah, they are the same thing. But, or is it? I'm just not going to think about that because that's not relevant. But a the direct sum of two modules is just the direct product of those modules, but it's the direct sum as abelian groups, so that's why it's written like this. For more than two modules, you write like this because this direct sum thing is a binary thing on is a binary operation on the category of modules, but it takes two modules and spits out a module. Whereas this is like sigma notation for addition over multiple things. It just condenses everything, especially if this is what's called an index set, especially if this index set is infinite, like with the case, well, I equals 1 to infinity. This is technically just I is within n. That's horrid. That's better. That's sort of a mix between the integers and the natural numbers. Or I is minus infinity to infinity, then you're just writing i's in z. That's the only other thing. The only other special notational convention there. Technically, this is the direct sum as abelian groups, but these are just abelian groups. But this is how you do that. So if you have some vector space, in fact, if you have some c to the n o plus c to the m, in fact 1 and 1, you just get to write it as a vector, well, because b's are both vectors, but 2 and 2, this is the first c to the m, this is the first c, it's the second c to the m, and you just are, well, it's this and then this, but 1, 1, 1, 1. It's kind of the same as 1, 1, 1, 1, but it's not defined to be the same, but it is the same for all intents and purposes, but it doesn't matter. But R over this is just you put R within everything, and it's like this. So, when we have a module which is the direct sum of a ring over and over and over again, then you can write it as vectors, and it's called a free module. And the 0th power of r is 0. You can technically have r to the infinity, but let's stick with finite finite rank free modules. It's not dimension because dimension is reserved for field modules or vector spaces. But but every module over a vector space is a free module, depending upon your set theory. But within most set theories, the axiom of choice is assumed. But this is proven usually with Zorn's lemma, where Max Zorn was a very, very intelligent man at the start of the 20th century who has a lemma which I'm not going to write down, but it basically says that if you have some partially ordered set, then any chain has a maximum, uh, where a partially ordered set is a generalization of the less than or equal to in well, less than or equal to in terms of partially ordered sets. Less than is total ordered sets. Oh no. No. Less than. So you can have a partial ordering on the complex numbers via just radiate out and write how far away you are from the origin. I'm just going to pause recording for a moment because I need to just head off for a second. Okay. Apologies for that. I just needed to go and look after my dog. Um, so I've talked about free modules and vector spaces. A module homomorphism is a map of the underlying sets, preserving the defining features of a module. So it's an abelian group homomorphism with this action preserving. So I want you to show that there is exactly one module homomorphism to and from this 0. This means, well, within category theory terms, this means that 0 is a 0 object, which the etymology should be obvious at this point, but, well, there's no buts. That's the etymology of that, and that gives you a very so there is at least one module homomorphism to and from any module, namely this. We'll also write it 0, but it should be obvious from context what is 0, the actual r to the 0. That's why I've kind of not written that. But usually when I'm talking about 0, I will just, well, usually if I'm talking about 0, it's either 0 to m or 0 mn, or indeed n to 0. But these are all zeros, but it doesn't really matter because it should be obvious that 0 here is actually just the map which goes... there's enough contrast. The map which goes like this, like this arrow is the same as this, then this. That should be very clear from context. So, we define an image and a kernel in exactly the same way, and we have an injective homomorphism if and only if. So that's another way of saying equivalence. That's the same thing as this, but this is quicker and this is so the double of a number is a multiple of 4 only if that number is a multiple of 2. And it's surjective if and only if its image is the actual thing itself, which should kind of be obvious. So if the kernel is just 0, then everything gets mapped parallel to one another, I guess. So no two things within M are mapped to the same thing in N, because if they are, then their difference would be 0, and that would just imply M equals N. So phi of M plus N, sorry, if phi of M equals phi of N, then phi of M minus N equals 0. Phi of 0 is always 0, just because reasons. Because phi of M equals phi of M plus 0 equals phi of M plus phi of 0, so phi of 0 is 0. Or the 0 within N, or the identity element within N. So phi of M minus N equals 0, so M minus N equals 0, so they are the equal. So the kernel is 0. Well, if the kernel is 0, then that works. But if the kernel is not 0, phi of M minus N equals 0, this just doesn't mean anything, because, well, you can always have phi of M equals phi of N not being 0, being equal but not being 0. So this kernel thing forces this to be 0. And there's an argument the other way around. And then well, everything within N gets mapped onto if everything in N gets mapped onto. So the image is a subset of N, the kernel is a subset of M. The same with ring homomorphisms. But we will write 0 for the unique map which goes through 0. So this is 0. This is also 0 because it's the map from M to 0 going through 0. And then this is also 0, but this is the 0 map going from M to N. I have seen this written, I will write in dark red again, I have seen this written as 0 and then a little mn here, but it doesn't really matter. It's just write 0, it's much simpler, and it's very clear from context because it's usually written within these diagrams, so m 0 n. It does. This is very obviously just the 0 function from m to n. There's no ambiguity, so there's no point unless you're actually writing 0mn, like within some proof. It doesn't matter. In terms of the elements, this corresponds to everything gets mapped to the identity element within N, which should make sense. But what I want to tell you is injective maps give you submodules, and surjective maps give you quotient modules. Sort of. Technically, it's equivalence classes of injective and surjective maps, but I'm if there is an injective map from M to N, then you can think of this as an inclusion map of M is included within N, and vice versa. If there is a surjective map from N to M, then M contains N some number of times. It just so happens that that number of times is fixed for this sort of category, but for module homomorphisms, for ring homomorphisms, for group homomorphisms, that is a fixed number of times. So you can say that M equals N over what? M equals N over something. And we will quantify how to do that in the next slide. So, remember, the kernel of 0 is everything, because 0, everything gets mapped to 0, and the image of 0 is 0, because 0 is the only thing mapped to. So, this next slide is fairly empty, but lots of space for me to actually write examples. So, a sequence of module homomorphisms is a sequence of them. So M to N to O, or M to M prime to M double prime. That is a sequence. Sometimes it's infinite, which, sure. But a sequence is a complex at a particular point if doing F and then doing G, which is this sort of circle thing, this is called composition. If composing G and F gives you the 0 from mi minus 1 to mi plus 1, and it's exact if the kernel of this is equal to the image of this. And sorry, I'm just thinking. Yeah, sorry. Well, the kernel is everything mapped to. Uh, well, if the kernel of G is equal to the image of F, then everything that's mapped to 0 from I minus, everything in mi which gets mapped to 0 in mi plus 1 is everything which mi minus 1 gets mapped to. So I have actually seen this. So you have some sets, and I've seen this as an image for an exact sequence, so you then have another thing within another set. But precisely everything which, and these are the identity elements, and then this is the image, well, that's also the kernel under G, so F, G, let's call this H. So it's exact at here if this is true. And then it's exact at here if this is true. You can, well, I am going to get onto that. Exactness implies being a complex, and I want you to show that, but that's just that's this explanation, but I've just show that more explicitly by writing out the kernel and the image, and then showing that G and then F implies that the kernel of G equaling the image of F implies that G circ F is 0, but that is just write out the kernel and the image definitions. But a short exact sequence, so I'm going to write SES, is of the form 0 into M into M1 into M2 into M3 into 0. So, and it's exact at all the middle points. But, well, exact at M1 means that, and let's write this as FG, and then this is obviously 0 and this is 0. But exactness at M1 means that the kernel of f equals the image of 0. And if we go back to the previous slide, the image of 0 is 0, which means that f is injective, because the kernel is the image of 0 is 0. And similarly, exactness here means that the kernel of 0 is the image of g, which, if we see, the kernel of 0 is M3, so the image of G is M3, so is 0. And then kernel of 0 is the image of G is M3. Oh wow! So this gives us 0. Well, this gives us F is injective, I think. Let me double check. F is injective. G is surjective. So M1 is a submodule of M2, and M3 is a quotient module of M2, and the exactness here tells us that, well, the kernel of G is the image of F. So M2 gets partitioned, let's say, into this many pieces. It gets partitioned into copies of M1, and those copies of M1 are precisely, well, one of these copies of M1 is the kernel of of the map into M3, which means M3 is M2 over M1, which means that we now have a way of quantifying, oh look, this one module is the quotient of another module. So 0, I, R, R over I, 0. That's how you write down quotient modules. And you're not just defining a quotient module in terms of the elements now, you're defining R over I to be the missing piece here. So if you have 0 into I into R into something into 0, this missing piece is the quotient module, which makes this a short exact sequence. That is how you can define quotient modules more, well, quotient ideals more generally. Or it's the ideal, but the module. We are technically working in R mod. That's the category, but again, we're not really talking category theory. But this is, well, this is actually used a lot within textbooks to just say, okay, we have some thing, we have some ring which we're working with, and we have, let's say, L. Well, IRL 0. L equals R over I. That's how this is written fairly regularly. And if you have a 0 object, then you have kernels and images, but you don't always in every category. This is why abelian categories were thought up. But the category of modules over a ring, that has to be an abelian category. In fact, you can have categories of complexes where you have a bunch of dots and you have a bunch of arrows, and the a I guess homomorphism of complexes is this this collection of arrows which makes these diagonal triangles. It doesn't matter if you go this way or this way. Uh, that's a lot. That's how a lot of different things are defined because hmm. So in a lot of maths, a lot of what you want to do is get a hard problem and rewrite it in terms of easy problems. So you have this hard operation and you have this translation thing, which is easy to medium, but you want to translate it to be easy. So that you can do this hard thing and then you can want these triangles to mean the same thing. um, this is I will probably do things on category theory at some point just because I mean I really like it. I really like category theory. I find it so rewarding. But another time in which, or another place in which short exact sequences arise is if you just have any module homomorphism or any ring homomorphism or any abelian group homomorphism. Well, remember, this kernel and this image, they are technically also of the same structure which you want. So the kernel of a module homomorphism is a kernel. The kernel of a ring homomorphism is a ring. Uh, the the ideal into a ring, well, that isn't a ring, but it is a module homomorphism, so hooray. But if you have some homomorphism of groups, rings, abelian groups, modules, let's stick with modules, just because all of those are special cases of modules. So a ring homomorphism is a special case of a module homomorphism because we have actually shown that an algebra is a module, and this is an algebra when we're talking about commutative algebra. So, if we have some homomorphism, well, the image is also a thing that's, let's call it M dash, and the kernel is also a module. I meant module, not thing. Let's call it M dash dash. Well, I now need to remember which direction things are. So kernel is actually a subset of M. So let's do that. This is a short exact sequence. Or given any homomorphism of modules, we have a short exact sequence. But I haven't told you a a very important fact, which are the isomorphism theorems. But one of the isomorphism theorems is quite literally just this is a short exact sequence. But this is abelian groups are modules, not groups. This is a this is a fact if you're working in an abelian category, which means that you're working with like okay. Sorry. The first well, I think it's actually one of the isomorphism theorems is M over the image of phi is isomorphic to the kernel of phi, or the other way around actually. Oh goodness. So one of the isomorphism theorems is M over kernel of phi is equal to is isomorphic to the image of phi. This is one of the isomorphism theorems for modules. But in other words, this is, well, curve phi to M to image phi to 0. This is a short exact sequence. Another thing is, given an exact sequence, so m I minus 2 into m I minus 1 into m I into m. Oh, and the sequence is a complex if this is always the case, and it is exact if this is always the case. I should have made that clearer. Oh god, we've gone over an hour. I will probably go over I plus 1, I plus I, into I plus 2. Okay, so, and then these are called boundary functions, so di minus 1, di, di plus 1, di plus 2. I don't know if I've gotten one off on this, but it doesn't matter. But given any exact sequence, you can have some short exact, a load of, well, one short exact sequence for every single thing here, where, well, the kernel of this is the image of this. Well, let's just stick to kernels. No. Or in fact, I should do this in a different color. So we have kernel of di going up. Yeah, it should actually be the, like, 1 over, but that doesn't matter. We have always got this. And within, and if we only have g circ f is equal to 0, then we have two different things at every single point, but then we actually start getting into homological algebra, and I don't want to do that just yet. I guess I can just, okay, 0 curve di 2. I think it's image kernel of di plus 1. One moment, let me actually let me see, because I do have this in Vakil's The Rising Sea, or if you just type into Google, if you type into Google if you type that into Google, you get the book which I'm referencing here. I have a physical one. In fact, this is one of the first ones sold. I bought it basically the day it came out. But I will pause and just find the actual homological algebra thing. It's in chapter 1, but one moment. Weirdly, it was the very first page which I got up. But the kernel of di to the, I guess, mi minus 1 to the image of di to 0, which I wanted to write anyway, but I didn't know if that was true. And then you have 0 into ha 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 image of di minus 1 into, I'm just going to write question mark into kernel of di into 0. These are two short exact sequences if we assume this is a complex. Um, I have written down a picture which shows both of these and the sequence, but it's it gets very messy, and especially if I'm writing it by hand. Last time I wrote it in a lovely website called Quiver, but I will. Oh no, 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 not here, not here, not here. I was looking at the wrong thing. There. Image into the kernel of di into question mark. I'm so sorry. Now that question mark measures how um how far away we have from an exact sequence. Or how far away we are from an exact sequence. And this is what homology is. Or cohomology, but it, in terms of just arbitrary complexes, they mean the exact same thing. You just swap all the arrows around, and or not even that, you just have this go in the other direction. I don't know if a descending sequence. No, an ace. This would be homology. Cohomology is because you start from 0 and then M1, M2, M3. Whereas if you're yes, and then it's a long exact sequence to the right if this goes on forever, and then it's a long exact sequence to the left if this goes on forever. And then M3, M2, M1, 0. Or the other way around, I don't fully remember, but I'm pretty sure that this would be an injective and this would be a projective resolution. But this is the homology at, well, here mi minus 1, but I've got my indices 1 off, but this is the homology at mi minus 1 here. I should really fix this, but I've already, I'm at 70 minutes long. But this is written hi minus 1 of, I guess, m, because all of these are m sub, but m and then that, just to show that it's a complex, but we've got all of the different things. So M bullet, or A bullet, or B bullet, or indeed at the top, because you tend to write I plus 1. Oh, in fact, it's I minus 1 here, because I was mostly working with cohomology because that's what's relevant to algebraic geometry. Because it just is. I definitely should introduce some category theory, because that's the angle which I have until now come at algebraic geometry from. I am doing a proper commutative algebra into algebraic geometry pipeline from now, so yeah. But my preference for quotient ideals or quotient modules is the short exact sequence way of writing it. Just because I've seen it in textbooks and it's more widely applicable, and that's kind of the goal in maths, is to make things as widely applicable as possible. so that you can go, oh, look, this tool kind of looks like this. Maybe I could use this tool and these results in this. So you're unifying various theories and fields. But now, this is, I guess, oh god, this I would say is an epilogue. Or should I go back to my red? I think I'll go back to my red. This is an epilogue of this entry. Just with one or two extra thoughts, just because it has occurred to me that the amount of algebra that one is expected to know going into a PhD or going into postdoctoral studies in general seems to be far less than it used to be. So, within David Eisenbud's commutative algebra, he is assuming that you know an undergraduate level of algebra, which I have basically done most of what is mentioned in a good undergraduate course, but this was written in 2004, and I never touched modules with it, or I never explicitly touched modules within my degree, other than writing it for my project, but my project was actually in it was supposed to be in algebraic geometry. It ended up just being mostly in category theory, and uh, I'm not going to get into that. It was mostly deriving delta functors from first principles, or using the snake lemma. From first principles would have required me using non-category language, and I kind of wanted to restrict myself to only using category language. So, using delta functors, or deriving delta functors. So that's why I discovered modules, but we never. Well, no. I was originally talking about sheaves over schemes, which I will definitely talk about later. In fact, I will, because I'm in the epilogue. I'm going to just be less formal and actually search through my book while I am recording instead of while I'm not. But yes, we do talk about this, or will talk about this in. Never mind, it's in the appendix. But what's called the snake lemma, where if you have some some pair of exact sequences, A, B, C, 0, and another, let's just say D, E, F, 0, and you have these. Okay, so let's call this alpha, beta, gamma, delta, epsilon, zeta, eta, theta, and iota. So if you have... Oh no. No, 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 no. I am so sorry. I was wondering why there were so many Greek letters. Again, I this is the epilogue, so it doesn't matter as much. So alpha, beta, gamma, delta, epsilon, zeta, and eta. If you have uh, zeta after alpha equaling gamma after eta, and the same with this, so eta after beta equaling delta after zeta, then you can have, wait, if this is exact and this is exact, then you have this exact sequence. So 0 to kernel of alpha to kernel of beta. Ah, I am so sorry. once again, I think this is called the restricted snake lemma because the actual snake lemma, you remove this, and then yeah, but this is a stronger result. Oh, so sorry. In David Eisenbud's, this is called the snake lemma, but it's actually the restricted snake lemma because you would remove this and this for the actual snake lemma. But yeah, but if 0 into A into B into C into 0 and 0 into D into E into F into 0 are exact sequences, and you have this property of this and this are the same, and this are the same from B to F and A to E, and this is called alpha, this is called beta, this is called gamma, then 0 into alpha, into kernel of alpha, into kernel of beta, into kernel of gamma, into, oh god, I haven't defined the co-kernel. The co-kernel of a morphism, so let's say alpha, is basically, you can define the kernel in terms of these arrows and dots, so I'm not going to, but basically that diagram you can flip all the arrows and then say the co-kernel has this definition, so in in fact, so the kernel of a function into a f b, and then say sorry, any m where this is the case, so this is an inclusion, but it this doesn't necessarily need to be an inclusion, but this has to be, or a injective function. So anything where any pair, so m and then mu from m to a, any mu such that f after mu is 0 kind of has a unique function into the kernel, such that this unique function, and then this is sometimes called the kernel as well. I usually write this as uppercase and this as lowercase, but this unique inclusion, so iota, kernel after this inclusion is equal to this mu. And then the co-kernel is defined if dually, but just flip all of the arrows and replace this with co-kernel. That's how you define it. Within within the category of abelian groups, I don't know if it's within the category of modules over a ring, but within the category of abelian groups, which I guess is the Z modules, but within the category of abelian groups, the co-kernel is of a function where f goes from a to b, is I think b over the image. So you actually have 0 image of f into b into co-kernel f into 0. This is an exact sequence, a short exact sequence as well. So that's required for knowledge of what I'm about to write, into co-kernel of alpha, into co-kernel of beta, into co-kernel of gamma, into 0. So these being exact and these having this property which is also called commuting, this commutative property means that this is an exact sequence. Now, if you remove this 0 and this 0 and just say this is an exact sequence and this is, then you just remove these zeros. And then this is exact. But there is some way in which you can say that this and this represent these HIs somehow, and then this is called the boundary map. So HI A into HIB into HIC into HI plus 1A into HI plus 1B into HI plus 1C. So this map and this map, oh, and this is sort of derived from 0 into A into B into C, where A, B, and C are complexes. or, yeah, are complexes. And these are morphisms of complexes, or homomorphisms of complexes, as I have described, basically, these squares. And then there's a third set of squares, so it's actually square, square. But these are somehow natural maps derived from this and this. This you need to either derive via, I'm not entirely sure, it's called something cones, MC. It's actually, if I get Vakil back up, it's within Vakil, but I'm not going to get Vakil back up. There is a way of deriving it from first principles, but you can somehow get you can somehow derive the snake lemma or the restricted snake lemma from, well, yeah, no, it isn't the snake lemma because this goes I and then I plus 1 and then I plus 2 and then I plus 3, such that the, oh, and then you have Ker alpha, then Coker alpha here, such that this is HI, this is HI plus 1, and then you somehow have this map. You can engineer a situation in which this goes into this. It's kind of contrived, and it's meant to be. This is the the conceptual shortcut approach to, oh goodness, the conceptual shortcut approach to deriving this. But that was the main theorem of my master's thesis. But let's talk about Epilogue Part 2, which is, as I said, within my degree, I did not actually reach modules for some reason. It's such a beautiful unifying theory and it's not talked about. I think it might just be because my lecturer really wanted to talk about finite fields and group theory and silo groups, and any abelian group A can be decomposed into the direct sum of z over n or plus z over m, where n and m are primes, and there's a unique way of doing that. So he wanted to discuss that and discuss group actions and this and that, but we didn't discuss modules at all within any of my degrees. So I took algebra in my second year. I technically took linear algebra in my first year, but that's just the study of vector space modules. So we did do module theory, I guess, the abelian group theory and linear algebra, but we didn't actively discuss modules, which I think is a massive shame because it unifies all of these things. But I took algebra, I took number theory, but it's number theory via algebraic methods, so via results in Euclidean domains and class groups over rings, etc. So it's actually when is Z minus D a unique factorization domain? Z adjoin minus D, so in fact we can define it better. So Z adjoin X over the module generated by D X squared plus 1. That's what this is. Or yeah, X squared plus 1. When is that a unique factorization domain? Well, sometimes it is, sometimes it isn't. So I took number theory, I took uh, Galois theory, which was really fun. I really liked it. I took representation theory. What else did I take? Markov chains, technically, but that's more probability. Well, even that, I took a broad range of topics in algebra, but I didn't learn what a module is. However, the word module in this context sort of appears in representation theory. So, a representation is some group homomorphism phi from a group into the general linear group N over C. This is sometimes called a linear representation, a complex linear representation, but this is what was called a representation within my module representation theory. Now this is technically a module over some ring called the group ring over the complex numbers here. So given C adjoin your group is, well, is that. But I'm not going to write it like that. Is the sum over the complex numbers, well, the sum over your group of some complex multiple of a basis element defined by that group, such that Ci is in the complex numbers, and such that, I'm just going to change that into a comma, EG multiplied by EH is EGH, where GH, this represents the group action. Modules over this are this general linear N, and this isn't a field. I don't think. There are probably cases where it is a field, but let's say is defined to be this is where I did touch modules, so this this homomorphism here is so you have rho of G multiplied by some vector. This kind of looks like you're taking a module of some ring. Well, you're taking a module over this ring. So rho of G times V is something within this general linear group. Well, is something, yeah. Rho of G is within the general linear group, so it's actually a linear function over the complex numbers. At some point, I don't think I did. Sometimes I start a recording and then think, no, I don't like the fact that I've just gone on a tangent immediately. Let's stick to the straight and narrow. This is kind of why I've done this epilogue thing, because these are tangents which I went on and thought, best not. I will just shear this off, and if I have time, technically I would have ended this, but I really want to discuss this because I find it interesting. But this row of G times V, this is a module from this CG into the, well, this is a module of this group ring into C to the N. So a representation of a group is some homomorphism from G to the D into C to the N here, but into some vector space V or W, and the dimension of this is the dimension of the representation. But you could just as easily write its row from CG into C, comma, C to the N, C to the N. With these, well, I'm just going to write pi instead of rho, just because that might be easier. Or pi of V, and then let's change this to V, where V is some vector space. You could just as easily write it in this form, where this G is technically kind of a general linear group over this, but not really. But yeah, I thought that this would be interesting. So a module over this is a representation, and I did study representations of finite and Lie groups. One was shake lemma. That's not what I intended upon writing. Snake lemma and Epilogue II was, I guess, a discussion upon modules within my degree, but let's just say modules of CG and defining what CG is. But yeah, I thought that that would be interesting, especially to me to say it aloud. I think I am going to definitely read more commutative algebra, just within now and next time I do a thing, but I mean, I'm leaving in 3 days, so I don't know how I will be able to, but it doesn't matter. I will record at some point. I might do a community post or two while I'm away, but otherwise I will definitely read more of commutative algebra. I had read a little bit of chapter 1. I don't know if I said it in this recording, but I am surprised. I think it is just a treat which they're giving you for, oh, look at this. This is the algebraic geometry which you're going to maybe do. But I was surprised by how much algebraic geometry was actually in this. So we start with, well, the actual origins of commutative algebra and follows its development through the landmark papers published by Hilbert in 1890 and 1893. Three major strands of the 19th century activity lie behind commutative algebra and are still its primary fields of application: number theory, algebraic geometry. The algebraic aspect really begins with Riemann's function theory, and invariant theory. I've been told actually that I should, well, that function theory, I got my F's and my TH's the wrong way round there. That function theory is actually something which I shouldn't learn, but I should look at as maybe an academic an academic curiosity. I might talk about that next time, but yes, I do think that this is probably a good place to finish, because otherwise I just won't.